Get it going. Rob 201, Calculus for the Modern Engineer, Take 8, Lecture 8. So we've got multiple types of limits now. So in this particular chapter, it gets into the full technicalities. You need to do all of calculus. So if you master these limits from the left and the right, you can do anything with limits in calculus, basically. And so the idea of taking a limit from the right is when you take h small and you decrease it to 0 through positive values, and you denote that by 0 plus. And so the plus sign there means that you're approaching x through positive values, so x values that are greater than x0. Similarly, the x0 minus on the limit, that means you're approaching x0 through values that are less than x0, so from the left. And so the formal definition is you fix x0 and then you take h through negative values and you increase it up to 0, but of course you never reach 0 itself, so you're never evaluating the function at x0. It's more compact just to talk about the limit as x approaches a point, and its definition is literally that both the left and right limits exist and are equal. So personally, when I'm applying this, I find it easier to think about left and right instead of just all at once. But it's kind of a taste thing. So these are sometimes called double-sided limits, but mostly people just call them limits, okay? Then the other ones, which are from left and right, they get a special designation. And then a function is continuous at a point when the limit as x approaches the point and the function value at the point all agree. And so you can do that in terms of double-sided limits or in terms of single-sided limits. Now, the big benefit is right here is in understanding continuity and limits carefully enough that you can decompose limit calculations into simpler atomic pieces. So many functions that we come across are compositions of functions. It's nice if you can recognize limits of simpler pieces to try to do that and then apply the function at that value. And this proposition says it works under the following conditions. If the inside function has a limit at x0 and the outside function is continuous at the limit point of g, then you can take the limit of the overall function by simply applying the limit to the often less complicated inner function g of x, and then all you do is evaluate f at that limit point. So it simplifies the process of computing limits. So that's why we like this particular value. And so what we're going to start off today is just practicing a bit more with that. And so before we do that, let's look at this graphical representation of what that proposition says. And so we're asking ourselves, does this limit exist? And I'm assuming, okay, let's say this function g that I'm not even making specific does have a limit at x0. Can I get the overall thing by just evaluating f at the limit point y0? And what I'm showing over here is if you take y0 equal to 0, where there's clearly a jump in f, because it is not continuous there, then the proposition fails. Okay, so we need f to be continuous at the limit point of g. Whereas on the other side, I just chose a really friendly value for y0. If the function g of x has a nice limit at x0 and it gets us y0, and then we look at y0 and we see the function is continuous at that point, then we can just evaluate the function there and we have the limit of the composition. So I've written the composition in two different ways, f of g of x and f composed with g of x. You see both. Does this work? Happy? Get the ideas? I'm going to find out, okay? Let's check it out. So I gave a challenge problem at the end of lecture on Monday. And so we're going to finish it up here. So the idea is we know how to define Euler's number. Yes, that number defined through compound interest that Bernoulli discovered, but then Euler really capitalized on it and built it up into a foundational part of mathematics, so he got to name it. The idea is once you have this definition of Euler's number, what is this limit if you replace 1 with x? And we're doing it for x greater than 0. I'm just emphasizing here that x is fixed. It's like pi or 17 or square root of 8, okay? Just a fixed number. N is what's varying here. X is fixed. And so step 1, we'll just give you a couple of minutes to complete this. Let's make a change of variable here. So I've copied the limit down here. Make a change of variable. We don't know how to handle this, but if it looked like 1 over m, so that's the thought process, we would know what to do with this. So introduce 1 over m equals x over n, and then you figure out that n is m times x. And then you see that n getting large is the same thing as m getting large. So with that piece of information, complete this. And so that maybe you don't go too far, what we're going to do in this next step is identify the functions f and g for applying the previous theorem, okay? So give it a shot. Luke online, if you want to punch something in. Oh, Jason's already on it. Oh, man. Okay, Luke, you got to compete hard there. Good. Okay, we've got an answer online already. Wow. Okay, let's get started. So the word limit is going to be continued, and there's going to be a parentheses, and we're not modifying the 1. So for the x over n, we're putting 1 over m. And then for n, we have m times x. Okay, how does that compare to this? Well, it's close. Okay, we got n instead of m. That doesn't change anything. big thing is m is scaled. So this is m goes to infinity. But when you have a quantity raised to a power, this is the same as limit m goes to infinity, 1 plus 1 over m to m raised to power x. Okay, so you can look in the book on power towers in chapter 1 to review your exponential rules, but that's how it works. As you keep taking higher and higher powers, if they're all just powers of the thing, it's just multiplication, and so you end up adding them all up on the exponent. Everybody got that? We're good? Okay. So we want to identify, we know this limit, and when we look at this theorem, then that tells us probably how to identify the function g, because it's the function where we know the limit, and then f is the thing on the outside that's being applied to the limit, and that's what's going on here. So identify f and g. We can have g of m, it's just the basic part of Euler's number, and that goes to e as m goes to infinity. So that's the point y0, e, when we're applying that. And then f of y is simply y raised to power x. And this function is continuous. For all y greater than 0, and hence it's continuous at e. And so we get that the limit n goes to infinity of 1 plus x over n to the n is equal to f of y0, which equals f at e. And so it's just e to power x. Okay, so we placed y with e. We get e to power x. Pretty cool? Semi-cool? Yeah, okay. So, those work out. I'm going to leave you a hard one for home that we won't work in class, but we're going to use it today. Limit h goes to 0 of e to the h minus 1 over h is equal to 1. So show that. So just like we needed a change of variable to get e to the x, that's the hint. Do a change of variable. We're going to let u equals to e to the h minus 1. And if you do that, so you add 1 to both sides, and then take the natural logarithm, you get h equals the natural logarithm of u plus 1. Okay? So add 1 to both sides of the definition. So this is actually a definition. add 1 to both sides, take natural logarithm. Then what happens here? H goes to 0. Well, if H is going to 0, e to the 0 is 1, 1 minus 1 is 0. So that's if and only if u goes to 0. So that's the hint. Play around with it. Use those, that change of variables, and then identify the functions f and g, and you should be able to evaluate this limit. Okay. Now we'll learn another way to do it a little bit later in the course that many of you have already seen, called L'Hopital's rule. It's easier, okay? This is the more fundamental way, and you don't appreciate the genius of L'Hopital until you grind out a few of these, okay? So that's the idea, okay? So yeah, L'Hopital is a really nice thing to have. Questions so far? Doing good on limits? Okay, we're going to apply limits, not do any more study of limits. Okay, so far in this class, we know how to do indefinite and definite integrals for monomials. I want to add one more class of functions to our skill set. And that would be that the integral from 0 to x of e to the y dy is equal to e to the x minus 1 for x greater than 0. And once we get it worked out for x positive, you can use the property that if you switch the lower and upper bounds on the integral, you simply change the signs. Okay, so there's lots of ways to treat it when you have x less than 0, but we're going to do it for here. Okay, so we're going to, I think it's our last time of doing a Riemann sum, okay? So either grit your teeth and bear it or enjoy it. That's your call, okay? I can't make that for you. Grit your teeth and bear it. So the integrand is continuous, so the Riemann integral exists. Okay. In fact, I'll even be more precise. It exists on all bounded intervals like this, x finite. Okay, so we don't have to calculate both Riemann sums. So that both Riemann sums exist and are finite, we only need to compute one. That's what the theorem says. Okay, so let's just get everything defined. I'm going to take a equals 0, b equals x. This is going to be the y-axis, and this is going to be f of y, and the exponential does something like that. Okay, so the first thing we do is we define delta y, and it's going to be b minus a over n, where for us, b is x, a is 0, so we get x over n. So that's delta y. Then once we have delta y, yi is I minus 1 times delta y. And for us, since a is 0, we'll have 0 equals y1 less than y2 less than dot, 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 less than yn, and equals b, which is x. Okay, so this is just how we would set up a Riemann integral. We're going to do the left one. It doesn't really matter. So the function is monotonic. So this would be xi, and this would be xi plus 1. Excuse me, yi. I said, boy, I'm so used to writing x. Those are y's. yi plus 1. All seems maddeningly familiar how to set up the problem, right? So if you're faced with it like you are in your homework, yes, this is how we set things up. And then area low n is by definition equal to the sum of the n rectangles we get by taking the left value times delta y. So this is because it's the lower sum. Okay, and so now it's almost turned the crank. We've got to plug in 1 to n. F of yi is e to the yi, which is I minus 1 times delta y. And then we still have delta y multiplying the value of the function. So that's the area under the lower approximation. Now, I'm going to use that e to the alpha x is equal to e to the x raised to power alpha to handle this product. Sum will become an integral sign. We've got e to the delta y, and I'm going to raise it like this. And the reason for this is that this gives us something that looks like a geometric sum. Okay, so we'll use this as r. And so this looks like we're adding powers of a variable from 1 to n. Now this is a constant. It doesn't depend upon I, so we can bring it out. And so that's what we're going to do. That's what we're going to do. You guys already did it. Okay, so delta y, and then the sum I equals 1 to n e to the delta y raised to power I minus 1. And now we're just going to start substituting in some of our definitions. So delta y is x over n. This is going to become r to the I minus 1 when I set r equals e to the delta y. Okay, so I can either look at this when I started at 1, this is taking r to the 0th power, then 2, that's r squared, and we go up to r to the n minus 1s. So we'll complete writing it like the geometric sums are written. So I'll do k equals 0 to n minus 1, r to the k. And k is equal to I minus 1. So we've done a change of index, just like a change of variable. Okay, so now it looks exactly like a geometric sum. And if you don't have the formula memorized, it's not a big deal, but you can always look it up. You get 1 minus r to the n over 1 minus r. And that's because it's a geometric sum. Okay, so just note over here on the side, we have r is equal to e to the delta y equals e to the x over n. So that'll be small, and we'll use it like h, okay? So when n gets large, h will go to 0. And then this is important, r to the n is e to the x over n raised to power n. And what does that give me? E to the x, okay? So this all simplifies down. And so we get area n low equals, after just a little bit of algebra, we have x over n, 1 minus e to the x, 1 minus e to the x over n. And what I'm going to do is bring this 1 minus e to the x as e to the x minus 1, so it's a minus sign here. And then this will be e to the x over n minus 1. So multiply top and bottom by minus 1 to flip the order, factor this one out, and then this depends upon n. And so we get that the integral from 0 to y, 0 to x of e to the y dy equals the limit as n goes to infinity of e to the x e to the x minus 1, then so you pull your e to the x. I keep wanting to put it in the numerator. God. Okay, and then here it's the same change of variable that we were looking at earlier, basically. So we'll let h go to 0. And then x over n, this becomes h over e to the h minus 1. And then that's that homework problem that you were given to work on for tonight. Sorry, this equals 1. And so this equals e to the x minus 1 as promised. Okay, so it's Riemann sums. This time we got a geometric sum instead of a sum of integers. Then it's just algebraic manipulation and then knowing this one hard limit. And that's the one I gave you all of the change of coordinates for. Okay, so that gives us the indefinite integral of an exponential when the argument is just y. Questions? Works? Got the process? Okay, so what would change? Take alpha, real number, and not equal to 0. Then we look at the integral from 0 to x, e to the alpha y dy. Okay, so instead of e to the x, the function has been scaled by a constant alpha that's non-zero. If alpha is 0, that's e to the 1, and then we just get x for the answer, which is not very interesting. So this turns out to be 1 over alpha, e to the alpha x minus 1. And so let's just sketch the proof. We won't do much. What this is going to do is set us up for doing changes of variables a little bit more formally later on, okay? We're integrating from y equals 0 to y equals alpha times x. Excuse me, y equals x, that's the limit. We need to deal with this alpha times y. Delta y is x over n, as we had before. And in the integral dy, it's really the limit n goes to infinity of delta y. Okay, so as n gets large, delta y goes to 0. Let's do the change of variable. z by definition equal to alpha times y. Okay, so we're trying to simplify this back down to the same function we had before. We know how to integrate e to the y, so with the change of variable, the whole purpose is to reduce this to, and that'll become e to the z, but we need to figure out how these variables change. Okay. Limits of integration. So if y is 0, then z is 0. And if y is x, z equals alpha times x. Okay, so z is alpha times y. We're just checking the limits of the integral. Limit, limit. So then we know how this argument change. We know how the argument changes. We know how the limits change. Let's make sure we understand how delta y changes. Okay, so when integrating with respect to z, if we formed our Riemann sums, delta z is still b minus a over n. So that's the fundamental formula. In the z world, b became alpha x, a is still 0, you have n. So this is alpha times x over n, which is alpha times delta y that we used before. Okay, so instead of doing y1, y2, yn, we're doing z1, z2, z1n. We repeat all of the lower sums, and then dz, limit n goes to infinity of delta z, and that's the limit n goes to infinity of alpha delta y, and so you get alpha times dy. So dz equals alpha dy. And I know, you guys already know it because you've taken Math 116, but this is how it gets there, okay? That's the thought process. And then hence, when you plug everything in, this integral 0 to x e to the alpha y dy, alpha y goes to z. When you do y equals 0, it's z equals 0. When you do y equals x, z equals alpha x. And then dy, it became 1 over alpha times dz, solving for dy. And so, sure enough, it's 1 over alpha. And then instead of plugging in x, we have alpha x and minus 1, and that's the promised answer. Okay, so our indirect integral tables now include monomials and exponentials with an arbitrary coefficient, alpha. If you use Euler's formula, that is discussed in chapter 1. Okay, so it says e to the ix equals cosine x plus I times sine of x. Or you can derive formulas for the cosine and the sine easily from the above. Okay, so what you observe is that cosine is a sum of two exponentials, so is sine. The only difference is now we're using the unit in the imaginary numbers, and you would need to go through and just redo this last calculation. It's done in the book if you're interested, but you can redo this last calculation and allow alpha to be not a number in the reals, but a non-zero complex number. And then from that, you get the integral formulas for sine and cosine from the exponential. You don't have to redo all of the lower sums, upper sums, etc. So. Okay. You guys have seen Euler's formula before? Yeah, perfect. And if you take 216, you just use it every single day. Let's take our break a little bit early, then we'll do the squeeze theorem, and then we're going to just think a little bit. No more writing. So we'll start back at 20 after. Okay, good. Okay, so let's get to our last technical result. It's called the squeeze theorem or the sandwich theorem, so it's pretty cool. And it's a pretty intuitive result. It says this: suppose you have three functions. One is less than or equal to the middle one, which is less than or equal to the upper one. Okay, so g of x is squeezed between or sandwiched between f and h. If the limit as x approaches x0 of f of x and limit x approaches x0 of h of x both exist, are finite, and equal to one another, Then what? Well, you tell me, okay? We're interested in what is the limit of g, but it's a really gnarly limit. But we can bound it by two simpler functions where we can calculate their limits. They both exist, and this limit are equal. So what is the limit of g of x then? It's squeezed between these functions, and the upper bound and the lower bound are equal. So then g is equal to either of them because they're the same, okay? Then limit x approaches x0 of g of x, and it's up to you. Just choose one. Yeah. Okay, so that's the picture makes it even more convincing. Oh, come on. Okay. Oh, here it is. Usually get these out so they're more quick to grab. Okay, so this function here, it's x sine of 1 over x. So it's kind of gnarly to figure out what that function is doing, because sine, as x gets small, x goes to 0. Sine of 1 over x is jumping up and down, but x is shrinking down, and so the bounding functions here, this is absolute value of x, and these are minus absolute value of x. And because sine is between plus and minus 1, you get that you can bound x sine of 1 over x between minus absolute value of x and absolute value of x. And then you take the limit as x goes to 0 of these two functions, they're 0. And because they squeeze or sandwich sine of 1 over x, you get the limit of x sine 1 over x, okay? So that's the sandwich theorem or the squeeze theorem. The problem is in practice, it's hard to find the bounding functions as always, okay? So, but we'll still find a very nice use for it later on. Then in Julia homework 4, you'll play with this numerically. So that's after the project. Okay, here's another idea. We know how to integrate continuous functions. Okay, suppose I gave you a wild function like this. Whoops, that's an open circle. Okay, so is this function continuous? No. So do our theorems for the Riemann integral apply? No. Okay. However, we're not dummies, right? We know that we're calculating area. We can break it up and integrate over this first piece. Then we can integrate over the second piece. Then we could integrate over the third piece, etc. So these are called piecewise continuous functions. Now we're adding two properties here. Notice that if we were calculating the limit as the values go to the left endpoint or the right endpoint, the way I've drawn it, these limits exist and they're finite. Okay? So wherever there's a jump, the limits from the left and to the right at the endpoints exist and are finite. So we're assuming AB can be decomposed as, say, A1 union, A1, A2 union, dot, dot, dot. To function is continuous on intervals like this. And then limits at endpoints are finite, exist and are finite. Exist and finite. Okay, so that allows us to extend the Riemann integral to a huge class of function. Anything that's piecewise continuous, you know how to integrate it. Okay, now if the function tried to do something like this and doesn't have a finite limit at the endpoint, so it just explodes like 1 over x does at the origin, then it's not piecewise continuous. Okay, you need bounded values at the endpoints. So, okay, so that completes our exploration of integration and most of the things about functions in this chapter. So here's the last piece, and you can get all this when the notes are posted. So it's up to you if you want to take a few small notes, but I would suggest you don't write a whole lot here. Okay, so we're going to do optimization, where we're going to try to find the minimum value of a function or the maximum value of a function. So let's see if we understand what max and min mean. We are going, when we did Riemann integrals in general, we needed max and mins to exist in order to define the upper bound and the lower bound. But here's the issue. I have f of x is 1 minus e to the minus x. What's its maximum value as x goes to infinity? 1. Okay. We have a proffered 1, which is great. So now we can start the discussion. Is there any value of x where f of x is equal to 1? There's not. Okay. So this is a key thing on the definition. We'll write it down formally, but this does not exist. We get closer and closer and closer to 1, but we never achieve it, okay? So if I was to say x star is the maximum, f star is the maximum value of this function, it doesn't have a max, because the max, there has to be a value in the domain. Now for this one, the minimum value, that's a little bit easier, okay? So minimum value exists. Let's do just a friendly amendment of the 1 minus e to the minus x. And now instead of being on 0 infinity, it's on minus infinity to infinity. What's the maximum value? It blows up to infinity. So once again, there's no number that I can assign to that. And the minimum value, it's getting closer and closer and closer to 0, but it never achieves it. So it doesn't exist either. So that's a bummer. Okay. So you can do the same thing for sets. Take this interval 1, 2. X is between 1 and 2. The biggest value of the set does not exist, a biggest number. And the smallest element of the set, it doesn't exist either. So that's very unsatisfying when the answer in 3 out of the, well, actually 5 of the 6 cases is does not exist. And so what mathematicians have done is they've added notions of greatest upper bound, greatest lower bound, and least upper bound. And these go by the terms infimum and supremum. And so here, as an example, what's the smallest upper bound for all elements of that set? Well, it's sitting right there in front of us. It's 2. And what is the greatest lower bound for all elements of that set? It's sitting right in front of us. It's called 1. And so this would be the infimum, and this would be the supremum. And so if you got that, then you've got everything else that I'm going to go through here a little bit more formally, okay? Greatest upper bound, greatest lower bound, least upper bound. This has a name, it's called the supremum, and that's called the infimum. So max and minimum versus supremum and infimum. Okay, so this function has no maximum value. It's the same example we did. So the key points on maximum and minimum is that the max and min of a set must belong to the set. In supremum and infimum, it's easier because we don't insist that the element belongs to the set. So 2 is excluded, 1 is excluded, but we still have a greatest lower bound, that's the infimum, and we still have a least upper bound, that's the supremum. Okay. So this is for the interval 0, 1. At the supremum of that set, it's the tightest upper bound. 3 is an upper bound for this set. 1.1 is an upper bound. 1.00001 is an upper bound, but 1 is the tightest upper bound. So that's the supremum. And then here, -7 is a lower bound for this set, but it's not a very tight lower bound. -0.01 is a lower bound. -0.00001 is a lower bound, but the tightest lower bound would be 0. And so if a set has a maximum, it's the same thing as the supremum, and if a set has a minimum, it's the same thing as the infimum. So here's the idea. X star is the maximum of a set if it's in the set and it's bigger than every element in the set, bigger or equal to. So that's the notion of maximum, but the key thing is it has to belong to the set. So it's the largest element in the set. For the supremum, the tightest upper bound, we're allowed to take X stars that are in R, but it doesn't have to be in A. So the supremum satisfies it's an upper bound for every element in the set. But if you find another upper bound, the supremum is the smallest of all of them. So it's the tightest or least upper bound. And then by convention, if you have a set that's unbounded, you just set its supremum equal to infinity. And if it's unbounded in the other direction, its infimum would be minus infinity. And the way those notions are applied to functions is we work with the range of the function. So here, we're looking at all the values of the function as x is varying, and so the supremum would be 1. It's the least upper bound. And then to help you out on your homework, I think it's for next week, you're going to have some examples like this where the set is written out, and your challenge is to find the largest element in the set. And so it's not just written as x between 1 and 2, so you can just see it easily. You need to look at this function, which is less than or equal to 2, and then find what are the x's that satisfy that bound on the function. And here we go through and give you a hint. You want 3x squared less than or equal to 2, multiply both sides by x squared plus 1. Cancel on each side. You've got 2 here, minus 1, you bring it to that side, it's 3. And so x squared less than 3, that's the same thing as absolute value of x less than square root of 3. Okay? Then once again here, max doesn't exist, minimum doesn't exist because of the strict inequality, but the supremum is 3 and the infimum is 3, minus 3. Okay, so if that's this homework problem, I'd suggest you work on it on your own, but you've got a bonus solution there. The main thing about maxes and minimums is they don't always exist. You need to to show that there's really an element in the set that achieves the upper bound or the lower bound. Supremum and infimum relaxes it. It can be an element of the reals outside of the set, so it's outside of the domain X or the range of the function f, depending on what you want, the maximum value of the function, or you've got some other type of set. And they're not going to play a large role, so that's all I want to do on them, to be honest with you, is let you be aware that these notions exist. And if we informally say max and min every once in a while when it should be supremum and infimum, it'll be a light tap on the wrist and no real penalty, because it's, for engineering, it doesn't make a lot of difference, okay? Now, if you want to go take Math 351 or Math 451, that distinction becomes the whole point of the course, okay? So then that's a little different. And what would you say if we just ended it up here? And if you guys have questions, help on homework or anything, Max and I can gladly stick around. But otherwise, let people out a little bit early. Okay? Any complaints with that? Just don't ask for a refund on your tuition, because I can't afford it, okay? So I'm going to be here and answering questions, so to make up for that. So super. So that finishes up chapter 4, where the hope was we would leave on friendly terms, and we'll start differentiation on Monday. And then when we get to chapter 6 on applications of the derivative, your eyeballs are going to get big. It's super fun. Okay, let me turn off the, thank you, Jason. Let me turn off the mic.